Welcome. We spoke last time about chemotaxis-induced phase separation. It's quite a modern topic, and it's one of those models that fall into the class of scalar systems that are distinct from thermodynamic systems. Today, I would like to broaden that class. So remember last time when we derived these kind of Keller-Siegel models, we started from a very simple model, namely something where particles move in one direction and then randomly flip back and forth between the two directions. And that gave rise to models like so that you see here on this slide. So let me now go to the board and discuss another class of models that brings us closer to what's called motility-induced phase separation. So the model we would like to discuss is a model that was formulated by Schnitzer some time ago. Actually, a very beautiful paper to read. If you want to read the original article, it's in Physical Review E some time ago in 1993. So it's quite a aged model. And it's along the same spirit as we talked about before. So we look at a one-dimensional system for simplicity. We say we have particles, and they now not only move with a tumbling rate going back and forth that depends on space. Now you also have a speed that is position dependent. And on top of that, we still have a tumbling rate that's also space or position dependent. The equations we would like to formulate is for two densities. So imagine you have a bunch of particles described by a density that moves in the plus direction, and you have another set of particles moving in the minus direction, and you would like to know the equation of motion for both of them. Then, as we had this before, there is a drift term, and there is a term that switches between the different directions. The drift term now is a little different from before because now our position, our velocity has a position dependence v of x, rho plus of x and t, and here it goes the other way around. It goes into the minus direction, so I have to change the sign and get a drift term that's the velocity times rho minus. Now, the tumbling rate I choose in a certain way. That's a factor of a half, which is just convention. So I say they flip to a minus direction with this rate, and they flip into the plus direction with the same rate. Right, so in distinction between what we had before, now the rates here are the same. And the other equation is just the analogous because it has the flips in the opposite direction. So there's a rho minus here, and I do have then a rho plus here as the second term. Right? So that's a very general structure, drift, and some switching between different states. As before, we argue in a similar fashion. We say we would like to have an equation for density rho alone. So we define a density of all the particles as the density of those moving to the right and those moving to the left. That's our total density. And because it's the total density you see from the equations, right, the terms that correspond to reactions, flipping the states, they cancel off. So that means our equation for rho of x and t has to be of the form of a conservation law, and explicitly it's minus dx v of x. And then there's a new quantity which is sigma of x and t that I define as the density of plus moving minus the density of minus moving particles. So this is what you get here, as you see by adding those two equations. And that is, as I just emphasized, that's a conservation law. So the term in the bracket defines a density. And if I miss it, I always mean that these quantities are functions of space and time. Okay, that's not all. That's the equation for the total density. You need an equation for the density difference between rho plus and rho minus. And this dt sigma of x and t is then, as you take the difference of the two, then of course things don't cancel out, but you get a term which is a drift term basically from the total density, v times the total density. And then all the other terms, they simplify to minus alpha times sigma of x and t. Right, those are our two equations. I have one for the total density. That's a conservation law. And I have a second equation for the difference between the densities. And that's also a non-trivial equation of motion. So you should notice, recall again, things that we learned about thermodynamic models, like Model A or Model B, especially Model B. There we know that the current is minus the gradient of a chemical potential, and the chemical potential comes from the gradient of a free energy. That's not the case here, right? This J here is related to the sigma, and the sigma is a dynamic quantity in its own right. Now, how do we proceed? Well, we could either solve those equations as they are, or we go about as last time, and we make an assumption about the speed of certain processes or the time scales that we have in the system. We say again that this flipping is very fast, so we can assume this equation for sigma to be equilibrated. So we look at times which are much, much larger than 1 over alpha of x, and then we can assume that this dt sigma is equal to 0. And then once we have that, the right-hand side is of course 0, and we can use that information to rewrite the first equation, that is the conservation law. So from that, if we just write it out, what we get from this equation, we get, solving the right-hand side equal to 0, we get sigma of x and t is equal to, in this approximation, 1 over our rate of tumbling times the gradient of v of x and rho of x and t. Okay, that looks like I would have something of the type of a gradient of a chemical potential, but it's not, right? This is a gradient now of a velocity times rho. So once you have that, we know that the current from this equation here, the current is just the velocity times sigma. So knowing sigma, we know the velocity. J of x and t is then equal to minus v of x divided by alpha of x. Oh, sorry, I forgot the minus here. Excuse me for that. Dx v of x rho of x and t. And this is now our constitutive equation, because once you know the current in terms of rho, you get a closed equation for rho. And this closed equation for rho has the following form. So closed equation for the total density rho of x and t. It has the form of tempo change of the density is equal to, as it must be, the gradient of x of this current that I just wrote down, v over alpha times dx v of x rho and x and t. Good. So once you have that, you would like to interpret what you just got. This is a bit awkward in the sense that we haven't had a structure yet that looks like so. But we know a structure where we have a diffusion coefficient times the gradient of a density. Okay, so let's try and just work this out by the product rule and then see what you get from that. As you do, what you get from that is an equation that's minus dx of a current, and this current has the structure of an effective diffusion constant times the gradient of rho, where the effective diffusion coefficient from working out these derivatives has the following form. D of x is v squared of x divided by alpha of x. And that's the same as before, just now with the generalization that this is a function of x. And if you look at dimensions, this is right. Diffusion coefficient has micrometer squared per second. As you work this out, you also get micrometers or length squared by seconds. So a note, I mean, this diffusion coefficient here has a kinetic origin. It's not a diffusion coefficient like in thermodynamics, where you have the Einstein relation, and where that's related to the viscosity of the surrounding fluid and kBt. There is no thermal energy scale here. Right? There's no thermal process here. Yeah?
There's two minus signs? Is this a mistake? Or
No, that's not. But thanks for asking. So that the idea is this is minus the gradient of a current. The current is the negative of the gradient of a density, because by Fick's law, you have the current always such that it fills up gaps. So it goes to lower values of the density. And if you take the two signs together, you have plus, and say d is independent of x, you would have plus Laplacian rho. And that's the diffusion equation. Okay? So it's right. There's two minus signs. The second term that you have has this structure. It's minus rho times v of x alpha of x dx v of x. Okay. And that has the structure of a drift term, right? This is a term where the current is proportional to the density times an object that's an effective velocity that you have in the system. So together what you get is a diffusion drift equation. All right, now you can ask lots of things about that equation. For example, you can ask what's the steady state as time goes to infinity. Steady state. So that means I want to know solutions where dt rho is equal to 0. This is the same as saying that in our system the current is 0. Current just being this object here. J of x and t, that's our current. Yeah, and when you solve that, you get a solution where if you insert what you know for d of x, which is v squared over alpha, then you should notice as you insert d of x, the alpha here and there, they cancel. And you get a equation, a differential equation for dx rho that only involves the velocity, and that you can solve by separation of variables. And what you do get is that the steady state solution that solves that differential equation is such that up to constants that I don't want to specify, that this object is 1 over the velocity. And that means that things accumulate where they go slow. This is not thermodynamics. Thermodynamics is independent of dynamic variables. It's something that determines the steady state by energy alone. So e to the minus beta, a free energy functional, is determining the solution in steady state. Here you have something quite unusual in thermodynamics, namely that things accumulate where they go slow, and slow and fast don't matter in thermodynamics. Of course, your everyday experience, if you go to Fußgängerzone here in Munich, is this window shopping effect, right? Where lots of people are, you will have a slowdown of the crowd. That's basically what this means. You get slowdown of this dynamic system where you have a already slow crowd available in the neighborhood. All right, questions? Good, and let's go to a topic that's very much related, and that's called motility-induced phase separation. And this has an acronym which is simply called MIPS. Yep.
One question regarding this non-thermodynamics behavior. But can we define like locally a thermodynamics equilibrium? Because then we can have an intuition like low energy and also low velocity, where particle can accumulate more.
No, this model is constructed, just from kinetic considerations. I haven't used anywhere in this any kind of concept like a free energy or an energy. So no. A priori, this has a different origin as a thermodynamic model. What we will learn, though, and that's part of what I'm doing next, that despite the fact that these models are derived without any reference to a temperature, you can, in some cases, arrive at an effective description that looks like right? That looks like a thermodynamic model, but it is not really, because I didn't start from a concept of temperature in thermodynamics. Right. Then let's continue here. So what I'm now trying to explore is, what if we have these kind of models where the position dependence of the velocity turns into a dependence of the velocity on the density itself. So like in my window shopping example, you have a crowd, there's a high density, and now let's assume that the velocity depends on the density of the crowd. If the density is high, let's say things slow down. So typically you would then say this is a monotonically decreasing function. And you want to know what happens with a dynamic system where you have such a kinetic effect of slowing down at high densities. The way I'm going to argue now is really trying to parallel what we have there. We say we have a crowd of objects and we want them to be conserved. So it means I have to have a conservation law that translates into a continuity equation with a current J. What do we take for the current J? So what's our constitutive relation for J of x and t? Here, as said, I try to parallel what we do have here in our model that we just analyzed. So I take something that has a similar structure as here. Let's say this alpha is now a constant, and focus on the role of the velocity being dependent on rho. So I take, instead of v of x, I take v of rho. And I just copy what we have. Minus v of x dx v of rho. Okay, that's our model. That's how we would like to define it. First thing I would like to discuss with you is to see under what conditions is a homogeneous state, a spatially uniform state, unstable. And that is something I can really just look at by considering the current. And let us write this out in the same way as we had it before. Let's work out the product rule. Then we have here minus v squared plus rho v of rho v prime of rho times the gradient of rho. Okay, when you look at that, it's a current. The current is proportional to the gradient of rho. Okay. So as you look at that, the term that you have in front is then an effective diffusion coefficient, according to Fick's law, where the currents are minus diffusion coefficient times the gradient in the density. That's a effective diffusion coefficient as a function of rho. And then when you start rereading the equation that we have here, it looks like a nonlinear diffusion equation, because now our diffusion coefficient is not a constant, it's itself a function of a dynamic variable. So when is this unstable? Well, it's unstable if diffusion does not do what it's supposed to do, namely leveling out gradients, but amplifies gradients, and that happens when diffusion coefficients are negative. So d effective of rho negative means you have an unstable homogeneous state. But if you look at this condition here, this means that what you have here is such that the time that the derivative with respect to rho of rho times v of rho is smaller than 0. Good. How else could I have obtained this result? The last time we worked on linear stability analysis, where we just assumed a homogeneous steady state, went to Fourier space, determined the eigenmodes and the eigenvectors, and that's of course completely equivalent. You can do this for your own. It's not a difficult exercise. You just look at these systems, you linearize, look at the spectrum, and then you get the very same relation as the one that I have here. This is just a shortcut, and it's much more based on the physics of the problem than the mathematics of a linear stability analysis. So the same as from a formal linear stability analysis. Now, when you compare to Keller-Siegel or model B, then those linear instabilities, they are associated with the spinodal, so with perturbations that grow on their own. And that kind of hints towards that maybe what we write down here could be written as a analogous problem that we had already, namely like a model B dynamics. So, but let's see whether that's indeed possible. Let's take an example to make this concrete. So let's say I take a profile for the velocity that's linearly decreasing, and let's focus just on the domain where this is positive. So it's have a linearly decreasing function which becomes 0 at rho star. Now, you can insert that linear relation here and do the algebra, and what you get from there is that the density needs to be large enough, larger than this value rho star, where the velocity becomes 0 by a factor of 2. So above that density, you will have an instability. And let's call this, for now, our spinodal region in quotation marks, because we don't know yet whether this is a true, has some clear analogy to thermodynamics. Good, now as promised, let us see whether we can rephrase this in a effective thermodynamic formulation. If we want to do that, we should obtain a form that is a thermodynamic form. And as you recall, then I must have that the current that I'm talking about is some mobility coefficient, m of rho, a non-zero coefficient that can be dependent on the dynamic variable. But then I must have an object which is an effective a chemical potential that also depends on rho. So now comparing to what we have, if we take the m of rho to be rho v squared of rho, then our mu effective of rho is the log of rho plus the log of v of rho. And you can check, right? You just do the math, do the derivatives, and then you find that this formulation in terms of a onset coefficient and an effective chemical potential recovers the same kind of current that we have here. Now, what's the interpretation of those terms? This is some kind of mobility. It depends on rho. Okay, let's put this aside for a moment. How would you read this? What's that? Exactly, that's an entropy term. And this one is then an interaction term. And that interaction term emerges because your velocity has a dependence on density. So, can we write this in terms of an effective free energy functional? Well, and the answer is yes, because this is kind of trivial in our case. This is just a function of rho, and of course you can rewrite a function of rho also in terms of a corresponding functional, because I'm basically finding the corresponding integral of the effective free energy. That becomes much more complicated if this term here contains any kind of gradient terms, which we don't have yet here, right? This is just a function of rho. Well, when you do that, as we just discussed, this will give the classical entropy term, rho log rho, minus rho. And then from the term that contains the velocity, I need to integrate that term from some initial value up to the point rho. And what I take here as initial value is my choice. That will just give a shift in the corresponding base value of the free energy density. So that means I can actually rewrite the dynamics that we have. dt rho of x and t is the gradient of m of rho delta f effective of rho d rho. Okay, so we do have a thermodynamic-like formulation that is somewhat reminiscent of our model B dynamics, not quite, because we don't have any kind of gradient terms that appear in the free energy functional. It's just local terms that have a structure that mimics an entropy and that have a term that mimics a potential. Good. Now let's see whether we can construct something more general. So let's say we compare this now to model B, and then by symmetry arguments try to generalize to other types of models. And for a change, let me use phi instead of rho as variables. And let's also go to general dimensions. Then recall that model B had the structure. It's the nabla operator divergence of the gradient of a chemical potential. And our chemical potential has the form of df of phi d phi, and that turned out to be, and the f where I put this, and the f of phi has a structure which is an integral over space, a local part of the free energy and the part that's accounting for stiffness effects. And that has to have a square. Right, that's our model B. And from that, you then get dt phi of r and t as I do the math. This is then, let's say, for simplicity, our m of phi is a constant. Then for that case, it has the structure m times nabla squared f prime of phi minus kappa nabla squared phi. Good. So that's the structure that you have when you have a purely thermodynamic model. And from the local part, as I just emphasized before, you can achieve a similar structure also in a non-equilibrium system. Now let's see whether we could, by symmetry arguments, also construct a model that has a structure which is not consistent with a thermodynamic formulation. And that's in the literature called an active model B. So let's see. We have mu equals f prime of phi minus kappa nabla squared phi. How did we get that? You go from here to there by taking a functional derivative. The f is just the derivative because that's the local part. This term here comes from the second term in the Euler-Lagrange equation, where you take a derivative with respect to gradient phi, and then you take another gradient of that. Okay? So if you think this backward, there's a one-to-one relation between this and that term. They imply each other. You can go backward and come up with that term given such a gradient. Now we can ask, what should I or can I write here as another term that's allowed by symmetry? And symmetry now I mean spatial rotational symmetry, the fact that you have a scalar that's of the same order, so all things are satisfied, but not that you can derive it from a free energy functional. A term that has the structure is a term that looks like so. It's a gradient of phi squared. It's a fine scalar quantity because it's a gradient squared, but you cannot derive it from a free energy functional. There's no way you can go this whole calculation backwards. So the new term cannot be derived from a free energy functional. Yeah?
Could you please specify more the symmetry? What symmetries are we considering now?
You can have still translational invariance in space, rotational invariance in space, and the fact that you're considering a scalar field. And then a term like so is allowed by all these symmetries. It's not forbidden, right? And that's why I'm writing it down. So if you allow yourself to step outside of thermodynamics, you can write it down. It's not consistent with thermodynamics because, as I said, you cannot write it as a functional derivative of a free energy functional. So it breaks fundamental thermodynamic relations. And as we know in biology, there's lots of processes like ATP hydrolysis that can potentially give rise to a deviation from a thermodynamic ground state because they drive the system away from it. All right, and that's active model B, this formulation. And when you take things together, again, our M of phi for simplicity is a constant. Maybe just put it to 1. This constant, then active model B is defined as a scalar field theory that has this structure. Okay. That's active model B. And what we will do after the break, we will ask ourselves what are the solutions of this equation? When does a homogeneous steady state become unstable? And what is then the ultimate non-equilibrium steady state that you get once you let the system evolve and become stationary? Recall, before you go to the break, in thermodynamics there was a very simple answer for the steady state. You just need to look at the free energy, look at the minimum of it, and you get the Maxwell construction. That's the answer in thermodynamics. Here you don't have a free energy, so it's not clear how you would construct the ultimate steady state. Right? You would need to solve the differential equation in the steady state to find out what the steady state is. And that's a very different reasoning than a thermodynamic reasoning where you have an extremal principle that gives you the result in a very simple one-line geometric construction. Okay. Good, so yeah, please.
Since we are not in thermodynamic equilibrium, how can we write down the velocity profile in the example of mobility-induced?
Say it again.
I mean, how are we able to write down the velocity profile since, I mean, we don't have the Maxwell distribution?
We don't, yeah. That's the question. I mean, the question here is, you have this equation of motion, and then you need, in order to find out what the solution is, there's no shortcut anymore. This is a dynamic equation. To get the steady state, you need to solve for the dynamics. And that's unusual, right? In thermodynamics, you don't have to do any dynamics to get the steady state. It's an extremal principle that informs you about the steady state. It's as simple as that.
I mean, also in the previous part, we shown the example where we can write down v of x, v of rho.
Yeah.
But is it just an example, or it's really?
It's an example. So I try to motivate from this example of a problem where you have crowding and where a velocity is monotonically decreasing in rho, that from that structure, from these kind of considerations, you can arrive at a model class that's very similar to a model B, but it's off equilibrium in two ways. One is that the origin of this local free energy functional that we have here, the F, is not coming from a picture of free energy, but from a kinetic picture. That was giving rise to this integral ds log of v of s. Second, and that's still thermodynamic in the sense that you can write it as an effective Lyapunov function. Here, this new term is not only coming from a non-thermodynamic consideration, it's also breaking the mathematical structure of thermodynamics. So you lose the gradient structure. At least the gradient structure in the sense that this is downhill on a free energy landscape. There's a very nice anecdote. So Einstein, when he wrote his 1905 paper, one of the three which are pretty famous in this special year of 1905, he wrote one on Brownian motion. And either in that article or in some other note that's available on the web, he says he doesn't get it, why you can do thermodynamics without even the notion of dynamics. And if you really think about it, it's weird, right? You can arrive at a non-equilibrium or equilibrium steady state without doing any kind of solution of a dynamic equation. You're used to this, but you should wonder why this is so.